Hello, my name is John Bargar. I am a senior scientist at SSRL, and I will be talking to you today about an introduction to experimental aspects of X-ray absorption spectroscopy. There are four major sections that I will be talking about today, which you see here. And what I've done is I've recorded each one of them as a separate video so that it's easy to go to each one, start at the beginning of just that section and play it. So I'm going to jump right into beamline components to get going here. So this section is really an introduction to beamline components, but I'm going to go fairly deep on some of the topics for those of you who already have some experience using this hardware. It'll help to explain why we use it and how you can optimize it. So there are several In-Hutch components that you're very likely to touch with your hands to configure, or you'll see the beamline scientists configure them, and you should know what the warning signs are if things aren't going well. These include ion chambers and the electronics associated with them, which are X-ray detectors, sample positioners, solar slits, cryostats, and sample heaters. And then there are a number of things outside of the hutch, upstream of the hutch, which are also extremely important to understand to help design your experiment, to help choose a beamline, and then also to help make sure it runs properly. Foremost, there's X-ray monochromators, but also you may be using X-ray mirrors actually either in the hutch or upstream of the hutch. So let's jump in here on these components. So this shows kind of a typical X-ray absorption spectroscopy experiment setup. And the X-rays are delivered into the hutch through the beam pipe. They enter into the hutch, and the first thing typically that they go through is an aperture defining slit, which is very important for quality control, data quality over the experiment, and a number of other factors, matching the beam size to the sample, for instance. Okay, so after going through slits, the beam goes through a pre-detector, which is counting the incident beam coming into the hutch so we can measure artifacts and normalize them out of the data. This is often referred to as the I0 detector for ionization chamber 0. The beam passes through this detector and then it hits the sample. So the sample is then, the beam can pass through the sample, and you can count the X-rays that are absorbed by measuring the signal in an ionization chamber downstream of the sample. And that gives you the transmission signal, the transmission X-ray absorption spectrum. But in addition, it's often the case that people measure energy calibration simultaneously using a foil that's located downstream of this so-called I1 chamber. So then an I2 chamber is added and the filter is sitting here, and that's what's used to, or a foil is used to measure energy calibration. So this is a pretty standard setup. So that's a transmission experiment I just described. In addition, it's very common that we use the fluorescence yield data because fluorescence is very strong. It's possible to measure especially metals in a sample at very dilute concentrations if you monitor the X-ray absorption spectrum, and you may do it either using a Lytle type ionization chamber detector, which is sitting here, or an energy dispersive fluorescence detector, which we'll be talking about more later. So let's start by talking about these ionization chamber detectors. They're pretty simple, but you can get them wrong if you don't know what you're doing. So this is kind of an end-on view of one of these ionization chamber detectors. You have an aperture. You can see a couple electrode connections going in. And these are connected to two large planar electrodes. One is biased a positive, the other negative. So one is here, and you can actually see the reflective surface of the other one right here. So you can see that electrode. And the idea is that this is filled with gas, typically nitrogen gas. And when an X-ray goes through it, it ionizes the gas. It releases an electron, which is collected on the anode, and cations drift and are collected on the cathode. And you can count the current generated as a result of this ionization. And why do we do this? So first of all, these are very stable devices. Second of all, you can use them to count billions of X-rays. You're not counting every single individual photon. Rather, you're counting the charge created by ionization of the gas in electric field. Very efficient way of collecting or measuring X-ray flux at high fluxes. Okay, I just want to point out that if you ramp up the voltage that's applied between these plates and just measure the signal that comes out of this detector, then you go through a ramp initially, and then you hit this ionization chamber level. And if you keep ramping it up, then you go through another set of regimes, proportional counting, Geiger counting, etc. So we want to stay firmly in the ionization chamber regime because we want to measure direct ionization events, not cascades. We want a uniform response over a wide energy range. We get that in this ionization chamber regime. But also, you can see here that the response, the intensity response, is very flat with applied voltage, which means that if your power supply is a little unstable, it will have a minimal effect on the signal. In other words, this is a very, very stable way of counting X-rays, and that's exactly what you need for an X-ray absorption experiment. Okay, this is a kind of an oblique view of these things. Here, in side view, you have X-rays going into the ionization chamber, your upper electrode, your bottom electrode. Depending on the energy range you run, you may want to fill it with a different gas. Below 5 keV, it's often filled with helium to avoid over-absorbing the X-ray beam. Between 5 and 25 keV, it's very typical to use nitrogen. Above 25 keV, you may use argon gas just to optimize the absorption for this length of the chamber. You can calculate flux using this equation. I have some of the parametric values needed to do this. This is something we do as a typical diagnostic at the beamline. It's actually a pretty cool thing to do every now and then and just see how different things affect the flux. I'm just leaving this information here so you can do it later by yourself. Also important is understanding how the signal coming from these ionization chambers is processed and knowing how to make sure everything's running happy so you get good data. So first of all, I should say that the current produced by these ionization chambers is really small. It's typically in the nanoamps to maybe hundreds of nanoamps range. And the signal cable carrying this out can act like an antenna. It can pick up RF pulses that are noise that's emitted by motors and other devices in the hutch. To solve this problem, we typically have a very short cable, so the current amplifiers that are attached to these ionization chambers are very close. They're typically sitting on the hutch table right nearby. And these things, so this is a typical SRS current amplifier. What it's doing is it's taking this very small current and converting it into voltage because we can send the voltage signal out of that hutch without a lot of interference. It's very easy to measure voltage. We can use a voltage meter, and in fact, if you're sitting adjusting the gains on the ionization chambers, you're looking at this voltage signal that's coming out. So we send the voltage signal into a voltage to frequency converter, and this converts the signal into a stream of TTL pulses. That's basically the frequency of the pulses is proportional to the count rate, and that goes to a computer and you count it. So this is pretty common overall setup. You'll find at different synchrotron sources, although some of it may be converted to digital form. Okay, very important is to understand that all these devices have a linear range, and you need to stay within that linear range in order to have good data. For these current amplifiers, it's less than about 5 volts, and that's why the beamline scientists are telling you may see a sticker on the gain control for the ionization chambers that you need to have, this signal needs to be less than 5 volts, because if it goes above that, you run a risk of losing your data because you just flatline. These voltage to frequency converters are most linear between 0.1 and 10 volts. If you go above 10 volts, you'll also flatline, but most people don't know it, in fact, because these current amplifiers are more sensitive. They're flatlining above 5 volts. But in fact, there is a linear range. You don't want to be collecting data with these at 0.004, as you see in this picture, because that's actually a fairly nonlinear range. You really want to be above 0.1 volts. So there it is. That's where all that comes from. How much voltage is enough? You want to have enough voltage applied across these plates from the high voltage power supply so that when you actively increase the voltage, you don't see that you're still ramping the signal. You want to be able to increase that voltage and have a constant current being collected by the ionization chamber. If you go too high, you're actually going to get arcing between the plates. It creates this clicking sound. You'll see sparks in the ionization chamber, and you'll have these infinitely large, infinitely short current events. So that's bad. This is good. Typically, the beamline scientist will set you up with this. Temperature control is extremely important for samples, and we have both liquid helium cryostats that allow you to run down to 4 Kelvin, as well as liquid nitrogen cryostats, which run at 77 Kelvin. These are pretty delicate. It's really easy to break these windows. For instance, the one that you see here at this point on this liquid helium cryostat. So use of these really requires training. They have to be very carefully handled. If these things blow up, they can really damage detectors that are sitting right next to them. So we have these available. Talk to your beamline scientist if you haven't used them before. Take your training, ask for retraining, and use them to good effect. Sample positioners are other types of extremely important hardware. In some cases, you'll have 7 or even 8 axes of motion on a sample, so it's more than just a single sample axis, as you see here. We also have sample heaters, so these can get you up to 800 Celsius. If you need these, again, talk to your beamline scientist. Okay, so then going upstream of the hutch, there's a couple very important things to understand. The first is the X-ray monochromator. The other are X-ray mirrors, which are used to condition the beam. Okay, why do we need to use a monochromator? So it turns out that the X-rays that are generated by the insertion devices, at least by a wiggler and a bending magnet, are polychromatic, right? You get everything from infrared light going all the way up to gamma rays. So that's no good for a spectroscopy experiment where you want to have a very well-controlled monoenergetic X-ray beam on your sample, and you want to scan that energy and control it very carefully. So this is what a monochromator does. It takes a rainbow of X-ray wavelengths, and it picks out of that rainbow one single wavelength, and it does that using Bragg's law. So Bragg's law says n lambda equals 2d sine theta. Lambda is the wavelength of the X-rays. D is the spacing for the crystal planes that you're diffracting off of in the crystal. And theta is the angle of incidence. So what you can see here is actually one of these double crystal monochromator assemblies that's warmed up so you can see it. The first crystal is actively cooled. The X-rays come in, they hit it, they diffract off of it, they bounce up. The second crystal is sitting offset and just above it. The X-rays bounce off that and go straight forward. So this is an upward deflecting monochromator. This is a very common geometry. Okay, so basically what Bragg's law is telling us is that if we have a single theta, right, then we're going to have a single lambda, or wavelength, or you can convert that into energy. So basically that is the good condition that we want. That's when you're passing the fundamental through. Unfortunately, n can assume values of 1, 2, 3, 4, 5, 6, etc. So if you have n simultaneously satisfying Bragg's law, then you will get higher energies coming through. These are called harmonics. So that's bad. We don't want those. So how do we get rid of them? How do we use this monochromator to get rid of them? And the answer is with a method called detuning. So what I'm showing you here is the intensity diffracted through one of these monochromator crystals when you rock the monochromator, just one of them, so the green curve here, just rock, let's say, the big first crystal through the diffraction condition on theta. You see that there's a range of angles over which it satisfies Bragg's law and diffracts, and then it goes away. So the big green curve is the fundamental. That's for n equals 1. For the n equals 2, for these higher order harmonics, what we find is that the diffraction curve is much more narrow. The rocking curve is much more narrow. And that allows us to cut that out by just basically detuning. So in detuning, we're taking this second crystal and we're rotating it off of the Bragg condition by a small amount. And that has the effect of displacing this rocking curve for the second crystal over, so that the intensity that passes through is now the integrated portion of these two curves. So this is the rocking curve for the first crystal and the second crystal. You see we've had to throw away intensity in order to do that. But you see, because the harmonic is so much narrower, we've lost a lot more intensity from the harmonic than we've lost from the fundamental. So this is called detuning. You're literally tilting the second crystal off of Bragg condition. It reduces the harmonics, but it doesn't eliminate it. And in general, as you go to higher energy, what you find is that the amount of intensity that you need to throw away is less and less and less. So if you're measuring chromium K alpha X-rays at 6 keV, then you need to throw away about 40% of the incident intensity, at least for these Si-22 monochromator crystals that we use at SSRL. Whereas if you're all the way up at 20 keV measuring, say, molybdenum K-edge XAFS, you really only need to detune about 15%. And this is shown in the so-called detuning curve. So this is the percent of the beam that you have. So 80% detuning means you're throwing away 20% of the beam by rocking that second curve off reflection. Vertical axis here is the percent of the harmonics in the beam. And you can see that as you detune, the percent of harmonics goes down, but eventually it becomes asymptotic. You really want to get out toward the asymptote before you stop detuning. So for 7 keV, you see you have to throw away about 30% of the intensity. But for 20 keV, you only have to throw away about 15% of the intensity. Alternatively, you can use a harmonic rejection mirror, which I'll show you in a minute, in which case, actually, you don't need to do any detuning at all. Okay, so the energy resolution of the monochromator is calculated from this set of vertical apertures that I described you on the second slide. So you have a set of slits that controls the height of the beam coming into the hutch. And if you project all the way back from those slits to the insertion device, which is producing the X-rays, it's typically about 15, 20, 25 meters. Then you can use that distance along with this opening height to calculate this very tiny angle called delta theta. And delta theta is very important because you can put it into the derivative of Bragg's law to get an expression for the energy resolution of the spectrometer. So that's just delta E over E equals delta theta, this small angle, divided by the tangent of the Bragg angle. So it's actually pretty cool to have this equation in your back pocket and just to look to see how different slit settings can affect your energy resolution. The main thing to say is that if you want to change the energy resolution, you can open or close these vertical slits. It has a huge effect on the edge shape and the apparent calibration, at least it can. So you have to be very, very careful when you do this. And in particular, you want to make sure that you are comparing apples to apples. So when you come to successive beam sessions on different dates, you really want to set these vertical apertures to always be the same so that you can compare spectra. This is a plot of uranium L3 edge XANEs at 3 different slit settings that give 3 different values of delta E, 30 eV, 10 eV, or 5 eV full at path max. And what you can see is that as this energy resolution changes, the shape of the XANEs changes quite a bit. In particular, the inflection point, which is often used to determine energy calibration, it's actually shifting. And look what happens with the maximum position of the white line. It's actually really sensitive. It's changing by quite a lot. So what I'm trying to say is that you need to be very careful to make sure that you have this slit setting constant between different measurements and really as small as you can get away with. Okay, just pointing out that you can choose different monochromator crystals for your measurements, for instance 220 or 440. The rocking curve width gets narrower when you go to these higher order indices, and the intrinsic energy resolution increases as a result of that. So for experiments where you need high energy resolution, you can choose a higher index monochromator crystal. All right, I promised you I'd talk about X-ray mirrors. So this is an X-ray mirror. This is basically a single crystal of silicon, 1 meter long, shaped a bit like a 2x4. And what you're looking at here is the long, thin edge, which has been polished to a very high degree. It's also coated with rhodium. And X-rays reflect off of this. It's also curved so that you can partially focus the X-rays. So we use these because by bouncing X-rays off of these, we can actually set a high cutoff energy so that any X-rays higher than that value will be lost. They won't bounce off of this mirror, and that's a way of eliminating harmonics. We can also bend the mirror to make the X-rays hitting the monochromator parallel, so that improves the energy resolution of the monochromator. Okay, so I just want to cover a couple basics of how these X-ray mirrors work. So what I'm plotting here is the reflectivity for 3 different mirror substrates: silicon, rhodium, and platinum. So as you go from silicon, rhodium, and platinum, the density of the metal or the metalloid is increasing. And what you can see is at low energies or also at low angles, you have really good reflectivity. The X-rays bounce off. But when you increase the angle of incidence on the X-ray mirror above a certain point, or alternatively when you increase the energy above a certain point, the reflectivity basically drops to 0, meaning that the X-rays aren't reflecting anymore. And so this is why we can use them to reject harmonics, is because for this specific case of silicon mirror, you can see that X-rays of 10 keV will reflect off just fine, but the harmonic, which will be at 20 keV, is not going to reflect at all. It's just going to go straight into the silicon mirror. So if you need to reflect X-rays of higher energy, in general you want to choose a more dense metal. So platinum is often used if you want to measure X-ray absorption spectra from heavy metals like cadmium or molybdenum or technetium. Okay, so that gets me to the end of section 1, beamline components. Section 2 is next, where I'll be talking about basics of transmission versus fluorescence detection.